Hello again. This is Professor Vijay Chalivendra from Department of Mechanical Engineering from University of Massachusetts, Dartmouth. This is the second presentation as a part of series of presentations I have been making on multifunctional natural fiber composites. This project is sponsored by National Science Foundation of United States of America. The motivation for doing this project as well as the fabrication of composites is not discussed in this presentation. I request viewers to go to the first presentation given in this link. In this study, we wanted to understand how the damage evolves in the composites under shear deformation. For that, we employed ASTM standard 3846. This standard provides a specimen configuration where we have two slots of 6.4 millimeters apart. These rectangular slots, in between the rectangular slots, we can induce the shear deformation when we apply a tensile load at the edge of the samples. We again use 4 circumferential probe measurement system to measure the electrical response in the composites as we apply the mechanical load. We have 2 outer probes where we supply the constant current. These probes are separated by 25 millimeters, and we have 2 inner probes that are separated by 10 millimeters. We measure the voltage change within the composite under far field loading conditions. So when we have a shear deformation, we anticipate to see a damage, interlaminar shear damage within the composite, and this damage can change the resistance of the composite. So for a given applied load, we should be able to measure the change in resistance through the measurement of change in voltage between these 2 slots, which are under shear deformation. This standard doesn't provide a shear strain expression. Hence, we have a schematic here that gives you how we measure the shear strain for the shear stress shear strain diagrams, which we wanted to plot. I will be discussing those in the coming slides. Now, we took a point in the shear zone, and this point can be represented with a small square, which is under shear deformation. When shear deformation happens, the square is going to become it's kind of a rhombus. Now, we measure the change in angle there with the help of the expression given there. In this study, we have experimental design where we wanted to see the different parameters, how these parameters influence the interlaminar shear strength as well as electrical response of the composite under shear deformation. So we have 2 different orientations, unidirectional orientation and cross-ply orientation. Unidirectional is 0, 0, 0, cross-ply is 0, 90, 0, 90. And we wanted to study the effect of amount of carbon nanotubes, which is 0.025%, very small amount, and 0.1%. The objective is to cut down the amount of carbon nanotubes because they're very expensive. And we also want to study the effect of carbon fiber length, which we reinforce them between the laminates using electroflocking technique. Again, I request viewers to go back to the presentation 1 to understand the process. And we also tried 4 different flock densities of carbon fibers of fibers per millimeter square of 500 to 2000 flock density, where we increase the flock density by 500 in increments. Coming to the results, I have interlaminar shear strength here. The interlaminar shear strength of all composites is shown in this slide. It is very cloudy. I will try to explain this one with the main points. The striking point, what you can observe from this plot, is that the unidirectional composites showed significant improvement in interlaminar shear strength compared to the cross-ply composites, because the unidirectional composites have a much higher contact area between the laminates compared to cross-ply composites. Now, let's pick a composite type of 500 flock density of 150, I think that is 1000 flock density of 150 microns carbon fibers, where you can compare the interlaminar shear strength of this composite of unidirectional composite with the cross-ply composite, where you saw a significant improvement, which is 400% increase in interlaminar shear strength when we change in the orientation from cross-ply to unidirectional. And one more striking thing we can see from these plots is there is an optimum amount of flock density, which is 1000 fibers per millimeter square, where from the non-flocking condition of 0 flock density, the interlaminar shear strength increases by 50%. the condition of 1000 flock density. However, with the further increase in flock density, the interlaminar shear strength slightly decreases by 10%. Hence, we can take 1000 flock density an optimum percentage. Moreover, for higher carbon fiber flock length, you see a slight improvement in the interlaminar shear strength of 10%. Hence, if I want to pick an optimum composite here, I will pick a composite of 350 microns carbon fiber long composite with 1000 flock density. That will be a good composite that can provide an optimum value of interlaminar shear strength compared to all other composite types. Now, to talk about electrical response, I would like to start with effect of the variation of CNT percentage. We have two different percentages as I discussed in the experimental design. We have 0.025% and 0.1%. So I pick a composite type here, which is the flock density of 1000 fibers per millimeter square and flock length of 350 microns of carbon fiber and flock orientation or the fiber orientation of 090, 090. So we have three different zones here. Let me focus on the zone 1 first. The zone 1 for 0.25% is very short compared to 0.1%. The reason for that is discussed with a schematic here, where when you have 0.025% percentage weight fraction of carbon nanotubes, you have very less number of carbon nanotubes in the system. Under shear deformation, these carbon fibers will actually make a new contacts with the neighboring carbon fibers. That's why you don't see any change in resistance during the first stage. However, let's take 0.1%. You have more carbon nanotubes compared to previous system, where you have 4 times amount of carbon nanotubes. Because of that, the length of the duration of the no change in resistance is much higher in case of 0.1% compared to 0.025%, because the neighboring carbon nanotubes makes the contact with the old carbon nanotubes. Now, coming to 2 and 3 zones. In case of 2 zone, the resistance change is much higher in 0.025% compared to 0.1%. However, in case of zone 3, where you can see a lot of fluctuations in the electrical response compared to 0.1%, where since we have very less number of carbon nanotubes in the system, the electrical network is not very rich, and you can expect to see a lot of fluctuations in the electrical response compared to 0.1%, where we have a very good conductive network compared to 0.025%. That's kind of expected from the amount of carbon nanotubes. The next one I want to discuss is the effect of flock density. Here we have pick 0.1% weight percent of CNT of 090 orientation of 350 microns carbon flock length. For this composite type, we wanted to investigate the effect of flock density. We have 4 different flock densities here: 500 fibers per millimeter square, 1000 fibers per millimeter square, and 1500 and 2000 fibers per millimeter square. Where let's focus on 500 per millimeter square. Here we have 2 different zones. As you can see, for all composite types, in the zone 1, there is no change in resistance as we discussed with the previous slide. Now, in case of 500 flock per millimeter square, you have a decrease in resistance compared to other 3 cases. The reason why we have a decrease in resistance because you have less number of carbon fibers and the conductive network is dominated by carbon nanotubes. We noticed similar thing in the previous studies, where if you have a system under shear deformation, due to Poisson's effect, the carbon nanotubes comes closer, and when they come closer, you will see a decrease in resistance. Hence, in the 500 flock millimeter square composite, where we see a decrease in resistance because this system is dominated by carbon nanotubes. As you increase the carbon fiber density in 1000 as well as other composites, where you start seeing increasing resistance because the network is dominated by carbon fibers, not the carbon nanotubes. Hence, you start seeing increasing resistance. Now, if you look at the maximum resistance value in the zone 2 for these composites, we see for the flock density of 2000 is much less compared to other composites. The reason is you start with a very low initial resistance for this composite system. As you increase the flock density of carbon fibers, the initial resistance of the system of the composite is very low. Hence, you don't see bigger change in resistance. Even though you induce the damage in the system, the damage is compensated by the lot of new connections you make with the neighboring carbon fibers, although there is a damage in the system. The effect of flock length. We have again system of 1500 fibers per millimeter square flock density, 090 fiber orientation with 0.1% CNTs. So we have two different carbon fibers in this study, 150 microns and 350 microns. As you can see, the zone 1 of the 350 microns is longer compared to 150 because of the rich conductive network you have with the 350 microns. So that's what kind of expected in this system. Again, when you look at the maximum change in resistance of the composite when the complete failure occurred, the 350 micron system has less percentage change in resistance compared to 150 micron system. This is again because of the reason that the initial resistance of the system of 350 microns is much smaller compared to the 150 microns. Hence, even though this damage is maybe similar or maybe higher in 350 micron system, the carbon fibers which are making new connections with the existence with the surrounding carbon fibers, hence you don't see significant change in resistance, although you have a lot of damage in the system due to the interlaminar shear. So to conclude, the unidirectional system showed 4% improvement in interlaminar shear strength compared to cross-plate system. In the flocking process, 1000 fibers per millimeter square showed an optimum level of 50% increase in interlaminar shear strength compared to no flock condition. During elastic deformation, we have not seen any change in resistance for all composite types. And composites having longer carbon fibers showed lower resistance change at failure compared to 150 microns because they have very low initial resistance before you start applying the load. Also, the flock density of carbon fibers increases the resistance change. As the flock density of carbon fiber increases, resistance change yet 2000 flock density, but the failure point is very small compared to other systems due to much lower initial resistance. So these are the main points of this study, and I request viewers to refer to this paper for more details on this study. I will be presenting the third presentation on the fracture studies coming up as a part of the series of these presentations. Thank you very much.